All right, so we've got this whole contraption set up with a larger block and a smaller block. The larger block's connected to a spring. There's a lightweight string connected over a pulley between the two blocks, and you're given a bunch of measurements. So let's just jump down to part A, which is to draw the free body diagrams for these two blocks. So for the large block, it is on a surface. So we're going to go ahead and start with the downward gravitational force and the upward normal force. And those two forces will be balanced. So I'm going to go ahead and put a little tick mark on them, indicating that they are of equal magnitude. And then we have a tension force and a spring force directed to the right and to the left. And those two forces are also balanced. For the hanging block, this block is smaller, has a smaller mass, so therefore a smaller gravitational force, so it should not be as long, and it has the upward tension force. And the tension force, since it passes over this kind of small, lightweight pulley, that tension force on the small block is going to be the same as the tension force on the large block. So we can put this with a double tick mark as well, and then those two forces are balanced since that block is also not moving. And that covers everything. In part B, we want to calculate the tension in the string. So we can look at the small block and just do Newton's first law in the y direction. Net force in the y direction is equal to 0. This just means the upward forces will equal the downward forces. Upward force is just Ft. Downward force is just Fg. And then we can leave the left side of the equation as it is. We can replace the right side of the equation with the formula for the gravitational force, m times g, which is going to be the mass of that block, 4 kilograms, times g, which is 10. And that will give you 40 newtons. For part C, we want to calculate the spring constant of the spring. So now we'll have to look at the first free body diagram, and the spring force is in the horizontal direction. So we want to set up Newton's first law in the x direction. Net force in the x direction equals 0. This means the rightward forces will equal the leftward forces. So we can just write the spring force is equal to the tension. On the left side of the equation, the spring force is just k times x. And the tension force we solved for back in part B. So I'll just leave the right side of the equation as it is. And then just solving this for K, the spring constant, that's going to be the tension force divided by the X, the amount the spring is stretched. The tension force was 40 newtons divided by X. If we go back up to the problem, we see that the unstretched spring is 0.20 meters long, but when the spring is stretched, it gets to a length of 0.25 meters long. So the difference from 0.20 to 0.25 is x. The stretch distance is 0.05 meters. So that's what we'll plug in down here. 0.05 meters, and 40 divided by 0.05 will give you that answer of 800 newtons per meter. All right, part D, we want to calculate the total mechanical energy stored in the full system consisting of both blocks, the spring and the earth. And we're going to use the table as the gravitational reference point for the large block, which means that the large block will have 0 gravitational energy since it's on the table. And we're going to use the floor as the gravitational reference point for the small block, and that small block is 0.70 meters above the floor. So the total gravitational energy is going to be equal to, now notice that there's no kinetic energy right now because neither block is moving. So it's just going to be the spring energy or the elastic energy of the larger block plus the gravitational energy of that smaller block. So the spring or elastic energy is given by 1/2 kx squared, and the gravitational energy of the small block is mgh. So we have 1/2 times the K for the spring, which we just solved for was 800 newtons per meter, times X, which was the stretch distance, which we just said was 0.05, and that's going to be squared, plus for the small block, the mass is 4 kilograms times G, which is 10, times the height above the ground, which is 0.70 meters. This first term right here, if we multiply all those together, that turns out to be equal to exactly 1 plus, and then if you multiply all this stuff together, that turns out to be 28. So 1 plus 28 is equal to 29 joules. Now we're going to cut the string at point P, which is over near the large block. And that's going to cause the large block to be pulled to the left by the spring, and it's just going to cause the small block to fall to the floor. So let's just calculate the time it takes the small block to hit the floor. This is going back to free fall kinematics. The initial velocity is 0. The acceleration is going to be 10 meters per second squared. And we're going to define the downward direction as positive since it's only moving in the downward direction. The distance, which is delta y, is equal to 0.70 meters, and we want to find the time. So t is equal to question mark. We are missing the final velocity here, so we're going to use the kinematics equation that's missing the final velocity. Delta y is equal to v naught t plus 1/2 at squared. The initial velocity was 0, so I can get rid of that whole term, and I can rearrange this to find t, multiply both sides by 2, divide both sides by a, take the square root, and we've got the square root of 2 times 0.70 divided by 10, and all that is going to give you the answer of 0.374 seconds. Now let's get the speed with which the block hits the floor. So I'm just going to continue this list from previously and just put v is equal to question mark. That's our final speed. And let's treat t as the missing item now, even though we know what t is. Let's assume that we just maybe have calculated that wrong. So let's leave this as our missing item and just pick the kinematics equation that is missing t, which is v squared equals v naught squared plus 2a delta y. The v naught, once again, is 0. And so v is equal to the square root of 2a delta y. This is going to be equal to 2 times a is 10 times delta y is 0.70. And we take the square root of all this stuff, and we're going to get 3.74 meters per second. And this should make sense because we could have gotten this much easier if we knew that for sure we had this answer correct. Since the acceleration is 10 meters per second squared, and it's accelerating for a time of 0.374 seconds, we could have just multiplied this 0.374 seconds by 10, and that would have got you this answer directly. For part G, calculate the maximum speed attained by the large block. So the large block is going to immediately be pulled to the left by the spring once that string is cut. And so in that case, we're not using kinematics. We have to use conservation of energy since we're dealing with an elastic energy being converted into a kinetic energy. So I'm going to set up conservation of energy. Ki plus ui is equal to k final plus u final. Initially, there is no kinetic energy in the system. It's not moving. And at the end, when the block is at its maximum speed, is when the spring is no longer stretched. So it's going to have an elastic energy of 0. So we're going to have the initial elastic energy is equal to the final kinetic energy. So that's going to be 1/2 kx squared is equal to 1/2 mv final squared. The 1/2s will cancel out, and solving this for v final, we're going to multiply both sides by divide both sides by m, and then take the square root of both sides to get v final. And that will give you an answer. Well, that will give you the numbers to plug in. 800 was the spring constant, 0.05 squared, that was the stretch distance. The mass of the large block is 8. So plugging all this in is where you will get this answer of 0.50 meters per second. So all this stuff so far has just been a review of kind of some old stuff, some new stuff. But now let's focus on the stuff that we just learned, which is dealing with the different systems. So for each of the following systems, we want to indicate whether the total mechanical energy of the system starts increasing, starts decreasing, or remains constant immediately after the string is cut. So when the string is cut, you can see that it's going to separate into these two things: the mass being pulled by the spring, the large mass being pulled by the spring to the left, and the small mass being pulled by gravity to the ground. So in the first system, it says we want to consider the system containing the small block and the earth. So in other words, ignore all of this stuff up here, ignore what's going on over here, and just focus on this small mass. So it initially has gravitational energy, but that gravitational energy is going to be converted into kinetic energy as the block falls, and there are no extra non-conservative forces acting on the system. It's just the conservative force of gravity. So the energy will be conserved the mechanical energy will be conserved as we turn this gravitational energy from the block into the kinetic energy of the block. All right, so erase all this scribbling out and go back down. And we're just going to say that this one remains constant. If we look at the system containing just the small block, then the only energy we can have is the kinetic energy, since we don't have the gravitational energy anymore. And that small block is going to be accelerating toward the ground, so its speed is getting bigger. Therefore, its kinetic energy is getting bigger, which is its mechanical energy. So the mechanical energy for this one is going to increase as the block falls. Now, if we look at the system containing the large block and the spring, if we go back up to the picture, we're kind of just ignoring what's going on all over here now and just focusing on what's happening right here. And you can see in this one that the elastic energy of the spring is going to be converted into the kinetic energy of the block, and there's no other things going on here. So this will be a basically it's like its own like mini little closed system right here where the energy is going to be conserved. So we can say again for this one, we can say that the mechanical energy remains constant between that spring and the large block. And if we look at the system containing just the large block, just like with the small block, it's just going to be the large block kind of moving to its right. The spring is acting as an external force pulling it to the right. So that means that external force is going to increase the kinetic energy, which is the total mechanical energy of the system. If we consider the system containing just the spring and nothing else, well, the spring is initially stretched, and now it's becoming less stretched when that string is cut. So because the elastic energy is decreasing, that is that's the only energy we have in the system is that elastic energy. So that's going to be decreasing. And for the system containing both blocks, the spring and the earth, since we're including everything now, this is a fully closed system that covers everything. And in a closed system, the mechanical energy always is conserved. So we can check that it remains constant. And finally, for the system containing just the two blocks, both the large block and the small block, immediately start gaining kinetic energy after the spring is cut, which we said right here and right here. Both of them start gaining kinetic energy. And so we want to know exactly why. Why does each block gain kinetic energy, even if the Earth, and I guess technically the spring, is not included in the system? This question is actually very similar to the last question that was asked on the 2023 AP exam. They mentioned taking the Earth out of the system and explaining why the kinetic energy of a certain system increased. So I just wanted to include it on here. And we can say for this one that the spring and the Earth both provide an external force that does positive work on each block. The spring is like an external spring force on the large block. The Earth provides an external gravitational force on the small block. So because we have these two external forces, each doing work on the block, each doing positive work on the block, that's going to increase their kinetic energy.